Hello everyone, nice to meet you. My name is Kwak. I am working at Myeongji College in Seoul, Korea. Today, I shall give a presentation to you. The title is A Case Study on Harbor Oscillations by Infragravity Waves. Co-authors Dr. Jung of KIOST in Korea and Professor Kobayashi of University of Delaware. At first, I'd like to introduce a study site. South Korea is here, and Japan and China is here. The capital city Seoul is here, and the study site Mukho located on east of Korea. East coast of Korea have a straight coastline. So their high waves act on coastline usually, and tidal effect very small. This is a satellite map of Mukho Harbor. This harbor have the oldest cement transport facility in Korea, and here this region is a fishery wharf, and this is Coast Guard base near the harbor entrance. Main wave direction is northeast. Waves deflected at the toe of main breakwater and then instant inside the harbor. And another wave was propagated shore protection, and then reflected wave instant inside the harbor. This harbor have a main breakwater length of 1,500 meters and width of 400 meters. We can see that this harbor very narrow widths and long harbor lengths. So this harbor has occurred frequently harbor oscillation by infragravity waves. The goal of this study is to investigate the measure of harbor oscillation by infragravity waves. At first we analyzed the 5 years field data and selected infragravity waves conditions for computer simulation. And then we carried out a computer simulation of wave field in order to find the target wave period. And then we proposed several layout plan or measures, and we compared response curves between before and after measures, and finally we found best measures of harbor oscillations by infragravity waves in this case study. The field observation has been going on for a long time using wave and tide gauge set up in front of harbor by KIOST from 2006 to now. In this study, we analyzed wave field data for 5 years wave field data. And then we extracted infragravity waves like this. This is a 5 years time series of infragravity waves from 2013 to 2018. The black line shows in wave height, HIG, observed from 0.01 meter and to 0.7 meter. And blue line shows in wave period, TIG, observed from 40 seconds to 130 seconds. We could see that high wave height shown in winter season when waves come from northeast direction. This is a scatter diagram of infragravity waves for 5 years. Wave period TIG concentrated between 45 seconds and 75 seconds. And wave height HIG mostly distribute on the 0.2 meter. In this study, computer simulation used Bushnet's wave model of Mike 21 improved dispersion characteristic. This is a simulation domain consists in 2.6 kilometer by 2.6 kilometer. The water depth distribute from 25 meter at offshore region to 8 meter or 4 meter inside the harbor. We simulated 7 wave direction from north to southeast and consisted input wave period of 64 cases between 30 seconds and 125 seconds with wave height 0.1 meter for each wave direction. Also, we set up 8 investigation points inside the harbor from P1 to P8 like this in order to compare response curve between before and after measures. I'd like to show you the results of response curves before measure at P1, P2, P4, and P6. The peak period appear on 36 seconds and 38 seconds at P1 and P2, located on inner harbor. But there is not appear the high amplitude at P4, located on middle of harbor. On the other hand, there is many appear the peak period at P6 near the entrance, and the harbor shape is rectangular. Peak periods are 32 seconds, and 68 seconds, and 110 seconds. Particularly, amplitude increased greatly on wave period 68 seconds when waves come from most wave direction. So, in this study, we are focused on this wave period. We are proposed a 5 layout plan of measures like this. Case 1, case 2, case 3, 4, and case 5. This is a layout plan of before measure that is present state. The measures consist in detached permeable breakwater with lengths of 120 meter and transmission coefficient KT 0.3 installed outside the harbor, shown in case 1 and case 2, and attached breakwater with lengths of 200 meter and KT 0.13 installed outside the harbor, shown in case 4 and case 5. Another type of measure reflects the vertical wall in a wave energy dissipator with 30 meter and reflect with 0.9 on 2 places in a harbor, shown in case 2, case 3, and case 4. Case 2 and case 4 consisted in combination of breakwater and wave energy dissipator. These figures show in a result of after measure. The black line shows in result of before measure, and the other line is shows a result of after measures. X is wave period, Y is amplification factor R, that is relative wave height. The amplification factor R shows in 4.49 in case before measure on wave period 68 seconds. This factor reduced in 3.26 in case measure 2. We investigate the comparison of type of measures, case 1, case 2, case 3. Case 1 install detached permeable breakwater K3, the reference the wave energy dissipator, and case 2 install both of them. The amplification factor R shows in 4.0 in case 1, 3.68 in case 3, 3.26 in case 2. We can see that in case 3, reference the wave energy dissipator, more effective measure than case 1 is told permeable breakwater outside the harbor. Also, we investigate the comparison of a different type of breakwaters. Left is told detached breakwater, length 120 meter, Kate is 0.3. Right is attached breakwater, length is 200 meter, transmission coefficient is 0.13. The case 4 have a more long breakwater length and more small transmission coefficient. We can see that both cases almost the same effective measure on wave period 6 to 8 seconds, like this. But in case 4, amplitude increased on wave period between 90 and 120 seconds, like this, because harbor characteristic length increased than before measure, due to installed breakwater in parallel with main breakwater. But there is not appeared increased amplitude in case 2. This table is comparison result before and after measures at P6 with a wave period 6 to 8 seconds and wave directions northeast. This is amplification factor R before measure, and factor R after measure, and reduction rate and percent. The most effective measure is case 2, reduction measure of this measure, 27.4. And next effective measure is case 4, reduction rate is shown in 23.6. On the other hand, in case 3, shown in reduction rate is 18%. This case reflects the vertical wall wave energy dissipator inside the harbor. This case more effective than case 1 and case 5. Case 1 and case 5 installed breakwater outside the harbor. I'd like to move to conclusion. At first, in this case study, the most effective measures of harbor oscillation by infragravity waves shown in case of install detached permeable breakwater outside the harbor and replace the vertical wall wave energy dissipator inside the harbor. Second, it is really effective measures of harbor oscillation if you install the breakwater outside the harbor just one time. Third, in case of replace the vertical wall wave energy dissipator inside the harbor, it's more effective measures than the breakwater installed outside the harbor. But there is a need to investigate it more detail about type of wave energy dissipator. Thank you for your attention.